That was very well behaved crowd. Welcome back, everyone. It's my honor and pleasure to introduce Lenka for our second lecture to look at computation through the lens of spin glasses.
Thanks, Julie. So I think that most people were here yesterday, so we will be kind of continuing in the spirit, but changing a little bit the topic. So the spirit was this, right? We are looking through the spin glasses, where we don't see maybe the full picture of computation, but the part we see it sharp, and we see it kind of, we can get maybe more details, more constants over there. So today, lecture 2, Inference, Learning and Optimization in High Dimension. And tomorrow is similar spirit, but today I will be covering learning with neural networks, generalization, overparametrization, and some generative network priors, and what that is about, a few more things. And the last two items I let for tomorrow. So tomorrow you'll be looking at the very simple model of attention and some spin glassy dynamics. So in high dimension, right? High dimensional probability distributions and energy landscape appear in machine learning, statistics, statistical physics. That would be the main fields. And when students ask me, okay, why statistical physics is the natural tool to study high dimensional statistics, I just tell them, look, we were just 70 years or so ahead of the others, because statistical physics, right, would establish something like 1910 or so, something like that. And in, say, statistics or machine learning, that came much later. So when the questions about high-dimensional neural networks and high-dimensional statistics came, statistical physics was ready. So they came in about 90s, and statistical physics had the tools to attack them. So these are some of the early works in high-dimensional statistics about learning from examples in large neural networks and first-order phase transitions to perfect generalization in a neural network with binary synapses. And I will actually be covering a little bit what has been in those papers. But right, the year, this is like 89, 90, 90. And now what is actually, why is the high dimension interesting? Well, because there's the limit in which, when yesterday I was talking about phase transitions, and we saw that these arise when the particles are numerous. And when things are numerous, things behave differently, and this is kind of, in this article, more is different. This is kind of philosophically put forward that more behaves different. The same is true in statistics, right? A lot of results that are true in classical statistics in low dimension just behave very differently when the dimension is high. So that's just like a generic thing. So some more, this was not like in years like 2000s, where neural networks were maybe not the main thing that people in machine learning would study. Physicists were not silent. They were writing textbooks. They were working on these things, but they were not kind of writing the whatever ChatGPT. So this maybe didn't attract the attention. But a lot of the theory that has been actually done back then, and these are some of the textbooks. So with this kind of introduction, why now you should be maybe curious about what's going on. Let's now get into a more concrete problem. So I will start with the basic case of supervised learning. What we are trying to do, we are, say, trying to classify pictures of cats and dogs. We are trying to teach a computer how to recognize from the sequence of 0 ones, because every pixel is just the sequence of bits. So what computer sees is this long number. And the task of supervised learning means that this long number for mu will be which picture I'm looking at. So there is the training data, which are n samples of d-dimensional vectors, and labels for each of the samples. For each of the pictures, I will have a label that can be real valued or binary. Here it's actually binary. And then the goal is to find a function, just mathematical function, from x to y, so that if the picture is a cat, it outputs 1, and if the picture is a dog, it outputs -1, right? So mathematically, this is what we are looking for. Now, okay, right, for a human it is trivial to recognize whether it is cat or a dog, but if you kind of don't know anything about neural networks and I set a problem like that to you, you go like, which function? Like, you know, square, polynomial, sinus, like this doesn't seem an obvious task. And so what neural networks do, neural networks are in a sense nothing else than a particular ansatz for how this function looks like. Right, so simpler object than neural network is linear regression, when you have points and you fit them with a line. Right, this may be in more dimensions. So in linear regression, you take this function and you assume that it's actually just the scalar product of some parameters that you will be searching times the vector representing the picture. That's all. Now, for instance, if you want to do classification, you want the output to be plus minus 1, this will output some real value. So you better add here some function, for instance, a sign to output plus minus 1s. So this would be called generalized linear regression. But there is still just one vector of parameters that you need to be finding so that the relation works. So you're looking whether there is a W so that this function works. This linear regression. A neural network, at least the feed-forward multi-layer neural network, is nothing else than very simple generalization of the idea, where now this function actually is the multiplication of this vector times now a matrix and a nonlinear function on the result, element-wise. And then you kind of imagine that this is the data again, and you do the same thing again and again and again, multiple times, multiple layers. And what is like this ansatz for a function parameterized by W is usually represented with a picture like that, where this is the input, this is the output. The connections correspond to the learnable weights, and these rounds correspond to the hidden neurons, as we call them. So, okay, a neural network is nothing else than a particular ansatz for the function. Then the way you train them based on the dataset is you just compare the outputs for a given W to the outputs that you would want, and then adjust the W with gradient descent so that you get closer, and that's it. So it's a very simple procedure what a neural network is and what we do to actually train it. Okay. And it does amazing things, right? So I like to give this example kind of deep learning in physics or in science in general. These are pictures from colleagues in EPFL, from the Swiss Plasma Center, from colleagues studying proteins, colleagues studying animal poses, or quantum physics. They do kind of amazing science using neural networks in the pipeline. And of course, this is much more. These are just some of my friends. And a lot more is happening, right? But do we actually understand very basic questions? So one basic question would be, how many pictures of cats and dogs do we actually need to be able to learn something reasonable, right? So for instance, here's some data set, the CIFAR-10, that is one of the classical benchmarks that a lot of kind of theory, mainly papers, kind of test in their in the papers is this CIFAR-10 with 10 classes, so there are airplanes, automobiles, etc. And for each of the classes, there is 5,000 examples per class, so 5,000 deers, 5,000 frogs, etc. And then we kind of, the state of the art is to get very good performance on this particular data set. And people are fighting for how low kind of, or high accuracy they can get. But we don't understand, like if you give me, say, 10 times less samples or 100 times less samples, like what is actually the best accuracy that is achievable? Are the algorithms that we are currently using actually close to it or far away from it? Is there still some place for improvement? One would kind of ideally think that we would have some theory that would give us what is achievable and we would be able to compare and see, but we don't have anything like that. We just don't know at all how many samples we actually need to get a given accuracy, like for a practical case like that. So that's something like that I would like to answer one day, but that I don't know how to do yet. That's too complicated. So we simplify. As we saw yesterday in sciences, when you want to understand something, you often simplify. So we will simplify here in 2 steps, okay? So the first one will already seem like a lot of simplifications, and then we will do even more. So the first simplification, we will we will actually assume something about the function from the x to y. We will assume this is not arbitrary function given by the world and something. We will assume something that should be much simpler to actually understand what's going on, because we will assume that the function that we are actually trying to learn, we will call it a teacher network, is itself given by a neural network of the type we are studying. So we are looking at the subset of all possible functions that actually take the form of the neural network. So this should be like a simple subset to actually understand what's going on. So what will be? So we have the input data x. So far we are not saying or assuming anything about them, and samples of the dimensional data. That's just the general setting. Then we pick an architecture and generate weights w star, and that will generate outputs y. And then the W stars, I hide it from you. So like yesterday we were playing these card games. So these W stars, that's the signal that if I gave it to you, you have everything, but I hide it from you. And what I give you, I only give you the pairs of x and y's. So I give you n pairs of x and y's. And I even tell you the architecture. That can only make your job easier, right? Or you can always pick different one if you think that different one is better. I don't give you the values of the W star. Your goal is to find some perhaps different W star, but such that the function is the same or really close to this function. Right? So this is already a simplification. We reduce to a particular set of functions. So now in this simplification, at least we kind of, so this is, you know, this kind of teacher-student setting. This was suggested, the first paper where kind of this was put this way in the context of the neural networks is this paper from '89 by Gardner and Derrida. And they studied it in a simple setting of a single layer neural network, so no hidden units. And also a specific case, they took this sign activation instead of generic activation. And the question were the same. So in a set, so I'm not like, so far what will be on the next slide is still kind of generic. There can be any number of layers, etc. And we are asking these two questions, back to these two questions. What is the best efficiently achievable test error? So how far our function is in terms of predicting the labels from the actual function. Kind of information theoretic question, this one. And the second question, if something is achievable, is it actually efficiently achievable? Do we have a polynomial algorithm that would do it for us, right? So yesterday we saw that these are not always the same. So we have these two distinct questions. So now, since I assumed a specific function of this form, at least I can formally write what would need to be written to answer these two questions. In the generic case, I don't know, but in this case, I know. I kind of can set things as a Bayesian inference problem. I can write the posterior probability distribution because I told you how I created the labels, given the weights and given the inputs. Right? That was, I postulated that the ground truth function takes this form. So that's the likelihood. And say that I also had some prior with which I was actually drawing this W star. So there was some PW from which I was drawing the W star. And then with the base formula, I just need to invert it. So now I formulate this here with probabilities, right? But if there was like no noise and the output was deterministically given by this function FW, then I can write a probability from it, kind of thinking of the Dirac delta function in a bit, you know, improper way, but morally we know how to do this properly. And the weights here are all the weights of all the layers, all the matrices, you know, all those. And then the base optimal prediction, what we need to do, we need to be algorithmically able to sample from this posterior and average over the weights the prediction for a new sample x mu. Right, so for Bayesian probability, this is the optimal performance. And this is generic. For the teacher-student setting where I kind of assume that the function, actually the y's, were indeed generated the way I assume them here to be generated. Okay, so of course this average takes in general exponential time to evaluate. So we are not really yet providing an algorithm, and we are not also yet understanding actually how well this does. But in principle, this is what we should do. Now note that this is not what we usually do in machine learning, right? In machine learning, we usually don't think about it in a Bayesian way and trying to average over the posterior. We usually do something simpler, that is the empirical risk minimization. We write some loss function that is some kind of distance between the labels we would want and the current output of the function. We maybe regularize or not, and we minimize over the W's, right? And these losses we can square, logistic, okay, this is what we usually do. So it's not the same thing. So in general, this is suboptimal, right? There is no reason this actually gives me the optimal result. So to keep in mind, right, what we are doing, especially when the dimension will be high, this is suboptimal. So we want to go after the optimal. Okay, so we know what to do, but this is still not enough to kind of do something very explicit. So what is done next, and here I take an inspiration in those old physics works, what are the other simplifications that are made? So this is stated in this slide, 1, 2, 3, three assumptions, right? And the talk will go that first I will tell you what's happening under these assumptions. And then the second half of the talk is what happens when we actually try to generalize these assumptions, right? So for the first half, okay, we will take the inputs random IID Gaussian. So not even arbitrary pictures, okay, just random IID Gaussian vectors, so no structure at all. Now the function will be actually just a single layer, no hidden units. So this is really just the generalized linear regression. Okay, this is the simplest possible neural network. In the original paper, that's what they did, and they took the sign here. And then the prior on how the weights are generated will also be some random IID, factorized. There will be some P of W from which I am drawing each of the components of these weights. And then we are looking at the high dimension limit, when the dimension D and the number of samples are both large, but the ratio is fixed. So that's where the high dimensional statistics kicks in. And that's the limit that allows us, this is a random process, everything is generated at random. But in this limit, the quantities that are interesting for us, they will concentrate on deterministic quantities, and that's what we will want to compute. Just like yesterday when we were looking at the density of the water or the accuracy in our spin glass game. So let's go for it. Now in those papers in the 90s, this was done using the statistical physics tools, such as the replica method and related. What we did when we started kind of working back on these problems some years ago, 7 years ago now, is that we actually proved that indeed these predictions from those papers were correct. And we proved it for a generic prior on the weights PW and for a generic activation function in this setting of a single layer neural network. And the kind of theorem has a similar flavor of what we have seen already yesterday. There is a function, the free entropy, that is shown on the next slide, such that in the limit, actually the optimal accuracy, the minimum mean square error on the test, so that would be on the estimation of the weights, which is very closely related to the test error. I will show the expressions next slide, is given by the global maximum of the free entropy. And then the accuracy that an algorithm that again will be some kind of message passing algorithm, but this time we won't call it belief propagation, we will call it approximate message passing because the underlying graphical model is dense, and that's how we call it when the underlying graphical model is dense. The accuracy of the algorithm will be also given by a maximizer of this free entropy, but the one that has the worst error. Because we start at random and we get stuck at the first kind of local maxima, if there are local maxima in this one-dimensional function. And M here is just a scalar. So that's the form in which this theorem comes. And now you're maybe wondering, how does this function look like? So this function looks like this. So the way it is defined is actually nothing else than the limit of the expectation of the logarithm of the normalization in the posterior. So that's the function you're interested in. And we show that it can be written in this limit when alpha is fixed and then both n and go to infinity. It's written like so. It's a sum of two terms. One of them depends on the prior, on the distribution from which we were drawing the teacher weights, the weights of the neural network that generated the data. And the other term depends on the activation. that popped out or popped in this P out distribution. And then this is some scalar integral over 3 Gaussian variables, or maybe over random variables that are drawn, again, scalar random variables that are drawn from the prior. Okay, it has this form that is not very transparent if you kind of haven't worked with it before. But it's some explicit formula of one variable that describes what is happening in the high dimensional limit here. And you know, if you are not used to working with the free energies, you are thinking like, what is actually the value of this logarithm of the normalization good for? It's a moment generating function. So from this you can deduce everything. For instance, from the maximizer you can deduce the optimal test error. It will have an expression that you can write using the maximizer. So again, the details I'm not showing, but it's something standard and you know, kind of elementary. So we have this explicit description of what's the optimal error, and here is the algorithm that you know that we are also describing. That's the approximate message passing algorithm. This is a pseudocode again. I'm not explaining the details, just to show you that it's just some iterative thing. T are the iterations that essentially uses multiplication with the matrix, or maybe it's element-wise square. But it's some kind of simple, you know, linear algebra-like looking kind of set of iterations. It involves these particular functions FA, FW, which are the proximal operators corresponding to these PW and Pout, which are some special functions, you know, some integral of a Gaussian times this scalar probability distribution that you can write up. And it gives you hence the variances and means of the weights and variances and means of the pre-activations, and iteratively you go to a fixed point, and then from the fixed point you can compute the base optimal prediction and the test error and all that. And depending, and then what we actually have, what we know, and these are works by largely by Andrea Montanari and his collaborators, starting with this paper by Boldhausen, where he figured out the proof technique to actually prove something like that, is that if we define how correlated the current estimator in the algorithm is with the ground truth, then as the algorithm is running, it follows an equation that we call state evolution that happens to be nothing else than kind of step 1 gradient ascent of this free energy. Sorry, this is supposed to be phi. I'm not changing the notation from one slide to another. The same free energy that popped up before in the theorem for the optimal error, right? So at one hand, we have this theorem about the state evolution that is telling us where the algorithm goes. And at the other hand, we have the theorem for the optimal error. They both involve the same expression for the free energy. Just one is the global maximizer, and the other one is the maximizer where one converges if one starts at m equals 0 with no correlation at all. So that's the only difference. So if there is a unique maximizer, this algorithm is optimal. If there are more, it is not optimal. And now we are kind of going back to a similar picture as we had yesterday. Okay, now this was like few slides with like the equations that, if one haven't seen them before, look pretty obscure. So if you wandered away, come back, because now you know you can forget about them, and let's go back kind of to the definition of the problem and what does this theory imply? How does it actually behave? So let me first show the case, because historically this was the case that the people in physics were most curious about, where the teacher function is this. So you take your Gaussian IID data, multiply them by a binary vector, and that creates your labels, okay? And now you are asking, what's the optimal way to learn it if the number of samples is this number, n over d is this number, so 1, 2, etc. And here is the test error. So if you have no samples, your test error is 1. Okay, no data, okay. And then it goes down, this is natural. So red is the optimal test error. At a alpha that is 1.245, there is a first order phase transition. Now you know what are first order phase transitions from yesterday, to a perfect generalization, where you perfectly learn the function. And the algorithm is lagging a bit behind, that's the green curve. It also has a phase transition, or spinodal of a phase transition, at a bit later point. and then jumps to the perfect generalization. So here, this phase here, there's the hard phase. There's the same type of analysis and result as we had yesterday for our card games. So here it is happening in the binary perceptron in a very simple neural network. What the blue points are, that's just the result of a logistic regression. Logistic regression is the first thing one learns about to analyze data, to classify in a supervised way into two classes. And logistic regression crucially does not know that the weights here were binary, so it's not picking anything like that because it's assuming the weights were generic. So that's just to compare. So at first it's not too far, and then it is far, but it's an unfair comparison. So that's first example. That was kind of historically important. People were curious about the phase transition. Yeah?
So what happens if you do logistic regression and you round the weights to plus minus 1? Is that getting better?
A bit better, maybe, but nothing much different. Yeah, morally the same as the blue points as they already are. But I will get to a case where they are not binary. There we will be able to compare more explicitly to like gradient descents, and it will be more fair comparison. So that's the third example. The second example is because that's the example that I showed yesterday when we talked about the compressed sensing, and I was showing you that we can destroy the hard phase by inducing the nucleation. So note that the compressed sensing is just a special case of our teacher-student setting here. Right? The data are, this is in the case where the measurement matrix is random IID, and the sparsity is reflected in the prior on the W. So with probability rho, or 1 minus rho, we actually have the W0, and with probability rho, we have it non-zero. And applying the formulas I just showed you, you get the phase diagram that I showed you yesterday. Okay, so now you have all the formulas to actually draw this. And you could, so that's just to connect to that. So that's a special case of our scenario. And then the case in which I will be interested most today is the case of phase retrieval. So that's again motivated by practice. When you do imaging with light, you actually measure. So light is a complex number, right? There is it's a wave. So you represent it with a complex number. When you measure it, you measure the intensity. So you measure the amplitude. You lose the weight when you measure it. So the losing of the weight creates an inverse problem of reconstructing the signal that is called phase retrieval. You kind of need to get back the phase because by measuring only the intensity, you lost it. So now, okay, complex numbers, I don't want to go into complex numbers. One can kind of get the interest of the problem already with real numbers when instead of measuring the x times w, I actually measure the absolute value. I lose the signs. So it's a sign retrieval, right? So it's like linear regression, but I don't give you the product, I just give you the absolute value. So it's, at the end you get again samples of x and y's, and you need to do linear regression, but you know that all y's are positive, right? All y's were the absolute values. So that's the phase retrieval. So again, it's a trivially special case of our teacher-student setting. The weights, the prior now is Gaussian, and the nonlinearity is the absolute value. This is the phase diagram. Here, there are actually a sequence of two phase transitions. One is of second order at half, where you start to be doing better than random guessing. And the other one is to exact recovery, exact or zero test error, that has the first order type with a hard phase. And the information theoretically, the phase retrieval starts to be solvable at 1, because that's easy to understand, because you lost the signs, the n signs, you lost them. But out of the 2 to the n possible signs, there is only one of them that will lead to an invertible linear system. So if you had exponential time, you could try all of them and one of them would work, and this is how information theoretically you would solve the phase retrieval. But if you do it with the approximate message passing algorithm, it lags a bit behind, and you need number of samples that is about 13% more than the dimension to actually, for this particular algorithm to work. Here, the asterisk here, it's an interesting case. This is not a problem that has a polynomial algorithm for some kind of trivial reason. Yet here in the noiseless phase retrieval, there is a polynomial algorithm for alpha bigger than 1 that is not a very efficient. It's like d to the power 7 or something like that, and it's a lattice-based reduction algorithm. It's kind of a curious case where that, you know, cuts the number of possibilities in which this hard phase precisely can be hard. So, for people probably already know, but this is an interesting case to kind of think about the hard phase. But that will not be my point today. My point today will be this, right? I now told you that now for this particular case, I answered my two questions. What is information theoretically achievable, and what is achievable with, say, robust and kind of low polynomial algorithms such as the AMP. But machine learning is not using any algorithm like that. Machine learning is using gradient descent, up to the point that the whole computer science department, when they study machine learning, they analyze the gradient descent. Okay, exaggerate a little bit, but right, everybody goes after the gradient descent. So a natural question is, okay, what happens with gradient descent? What's the performance of gradient descent in this example? That's where it gets interesting. So few slides, actually, when we have this hard phase, like we have this paper a couple years back that actually surprised us, and it can be summarized in one sentence, that when there is the hard phase, that kind of creates hurdles for gradient-based or Langevin-based algorithms, in the sense the hard phase for these algorithms will be even bigger than for the approximate message passing algorithm. So we predicted that. Here I'm, in a sense, commenting the hard phase is glassy in some sense, and this glassiness extends to its vicinity, and this is what causes the hurdles. For the approximate message passing, it ignores the glassiness. That's kind of the beauty of the proof of the state evolution, that it, in a sense, physically follows the non-physical spin-orbit, but that's what it does. That's what makes it work better. And in some sense, optimally. There is this interesting line of work that shows in which sense optimally. And then the consequence that we predicted in this paper is that the kind of algorithms that walk directly in the space of weights actually have even larger hard phase than the approximate message passing. And this gap surprised us in physics. It was not anticipated. The anticipation was that where the AMP succeeds, that's also where the Monte Carlo or Langevin or maybe gradient descent will succeed. So actually, when we came up with this paper, colleagues in physics did not believe it, so we needed to do kind of more and come up with a simple model where we can actually establish it more firmly. The model where this can be established very precisely, but okay, so far without like not rigorously yet, is a variant of these low-rank matrix factorizations that we talked about yesterday, where this time I have a matrix that I measure and also a tensor that I measure, and I observe on the same signal the matrix and the tensor, and then try to reconstruct the signal back from it. So again, now we are familiar with phase diagrams. That's how, depending on the two noises in the matrix and the tensor, there is the impossible phase, there is the hard phase for the AMP, there is the easy phase, but there is additionally a phase in which the Langevin algorithm that is going after the base optimal estimator actually also fails. And we have an explicit prediction for the line at which it fails. And kind of theory that leads us to that prediction. So we see that there is a larger hard region when we run something like Langevin. For gradient descent, it is even worse, because that's not even going after the base optimal estimator, but after the maximum likelihood that in high dimension is generically suboptimal. But back to the phase retrieval. This is just a generic argument that we expect that something kind of hard appears here for the gradient descent. So in the phase retrieval, we don't have like a crisp closed form analysis of the gradient descent, but we can, this is by the way how the gradient descent looks like, right? The natural loss for the phase retrieval is, we know that y was the absolute value, so natural loss we can write is actually, we know that. So we take a square here and a square here, and we are kind of comparing the right things. And now we try to minimize this loss with respect to the weights, W, just running the gradient descent with with maybe discrete steps or whatever protocol one kind of likes. And we can definitely do numerics. So this is some plot where we plot fraction of success of recovering the function exactly for different sizes of the system. We kind of see as the system is getting bigger, the success comes less and less often as a function of the alpha, that is still the number of samples over dimension. So it starts working somewhere at 7. So just to summarize what I am saying here, right? Gradient descent in the phase retrieval. So we have 1 that is needed information theoretically, 1.13 where this approximate message passing succeeds, roughly 7 where numerically kind of gradient descent succeeds, and then we have some proofs about conditions under which we can rigorously prove that actually gradient descent succeeds. That is some large constant or some polynomial of log d, so much bigger than 7. And just a note for those that are kind of used to see machine learning talks, and a lot of the theory is developed in some kind of kernel regime or NTK regime or Gaussian processes, all that, right? All these kind of ways of solving things here would require the alpha to be of order d. So this is alpha of order 1. We would need additional factor of d times more samples, so much more, right? So here we are in a non-trivial regime where we are kind of non-trivially changing the weights and learning the features like far, far away from these kind of linear regimes or kernel regimes where simple methods like that can work. Okay, but there is this huge gap between what we can get and what the gradient descent gets us. So that's frustrating. So what can we do about it? Well, deep learning is also overparameterized, right? We always run these neural networks with actually much more parameters than we would think we need to. So we get things like that, right? The kind of traditional bias variance trade-off where you say, here I am fitting some sinusoid with 2 ReLU neurons, 5. 5 look quite good. I have 10 points, it looks close. When I am fitting by 10 ReLUs, the test error is horrible. But when I'm fitting with 500 ReLUs, it's perfect. Right? We see kind of this Benheim overfitting that is not happening, and that comes from the overparameterization. So there has been a lot of works to explain that in the kind of setting of kernels and linear methods. So let's now look, let's try what we actually get from the overparameterization in the phase retrieval. So what that means is that we just change the loss function that we are actually minimizing by adding here m hidden units, like in the plot with the flashes, that this would correspond to this. And instead of optimizing over 1 vector, we optimize over m d-dimensional vectors. But we still know that the true function was this one. We just did not know, we just do not know the value of W star. But we know there is only 1 W star, and that it's just the scalar product and absolute value of it. So both from a Bayesian and from a physics point of view, this is crazy, because in physics, when I know something is true about my system, I want to reflect that in the model that I use to study my system. I will not intentionally put more degrees of freedom in the model that I know they are. That doesn't make any sense. Right? So from the science point of view, doing something like that doesn't make any sense. Okay, let's try anyway. So if we do it and we take the m bigger than d, we can actually prove the following thing, that when we have twice more samples than the dimension, this landscape trivializes in the sense that there will be a single global minima, and moreover, this global minima generalizes well. So it gives us the right function. It's not just some spurious thing. So this we can show from this paper with my former student Stefano and Eric van den Eyden. So there is this magical threshold too. And also, there is nothing tricky happening here. We can show that in randomly initialized gradient descent actually goes to that global minimizer, and it agrees nicely with the numerics. So right, we have this threshold of 2. So if I return to this picture that was summarizing things, now gradient descent run in this illogical overparameterized case does actually better, considerably better, than the gradient descent run on the logical loss. So this is what happens with the overparametrization. To me, this is a really kind of nice illustration of the role it plays, right? Now, note some comments. So first of all, the comment that I already said, this is deep in the feature learning regime, as people would call it, because we would need alpha of order D for linear methods, such as kernel methods, to even start doing something, okay, one thing. Second point, if you are, say, at alpha 3, so somewhere where the gradient descent doesn't work yet, but the overparameterized does, imagine the following kind of thought experiment. You start with few parameters, just a little overparameterized, and it doesn't work yet. Then you put more and more parameters, and it starts now suddenly working, right? And there is this emergence of things working as the number of parameters grows. This is something that we hear about from the practitioners, that they see that in the state-of-the-art neural networks. So this is a toy case where we see something like that. Third point is that despite needing this overparameterization to actually get to the right function, now if we are at the right function, we can generate more samples. If we had more samples, we could have solved the original problem. And this way, we would actually distill the overparameterized network into the small network with just the D parameters that it originally had, and we even were given that, right? Because the teacher told us the architecture of the network. We were in the simplified case. So we can distill this overparameterized network to a network that somehow has the right number of parameters. So again, something that we see in practice. And the fourth point is I think the most interesting, because if you ask back, what happens with the approximate message passing when you overparameterize? It's not getting better. This proof that I was citing by Montanari's group about optimality of the base optimal approximate message passing covers that case. Nothing can improve the threshold 1.13 in that class of algorithms. So with the right algorithm, overparameterization does not help. It helps if we are using kind of this suboptimal algorithm as gradient descent. So would it be that actually the overparameterization is a byproduct of the fact that we are using the wrong algorithm to train these neural networks? Like in this example, it seems like that. So I think that's an interesting thought kind of generically, whether this could generically be true in neural networks. Because of course, I mean, the fact that they need to be so huge, that costs all that like power that we are burning. If we could do it with the same, with much smaller networks, smarter algorithms, that would be awesome, right? I am not saying that this is telling me how to do that, but this example kind of questions whether this is actually something that we should very definitely aim for, because it's just calling for it. Okay, let me get to the kind of second part where I want to go back to the assumptions. So what were our assumptions? We were using the data that had no structure. Well, real data have structure. The priors that were IID. I will get why it's interesting not to do that. And the single layer. So let's start with the priors, because that's kind of an interest. So these are kind of 4 points in which we'll be generalizing the assumptions. The fourth one will definitely be tomorrow. Okay, we'll see about the third one. The fourth one definitely tomorrow, when I actually not take the fully connected layer, but take a layer with the attention mechanism. But let me start with the first point. What if we actually think better about the prior? So this is interesting in the following context. There is this series of works from 7 years ago or so, where generative priors were suggested instead of the sparsity. I already mentioned a bit yesterday that this idea of compressed sensing brought a speed up of roughly factor 2.5 in the kind of commercial MRI machines. And using the generative priors instead of the sparsity brought an additional speed up of roughly 2 to these commercial MRI machines. And this is one of the key papers in the area of MRI that was bringing that forward. About the same time, there was a paper by Alexis Dimakis' group bringing that forward in the context of compressed sensing. And yet, kind of within a few months of that, or even a bit before, we had this theory paper where we were not aware of this nice connection to the generative priors, but where we wrote what needs to be done with the approximate message passing and this kind of line of solving the mals so that it works. So what are these generative priors about? Is that in the context of the compressed sensing, where the W star was the signal, instead of assuming that there is the wavelet basis in which pictures are sparse, we assume that there is a generative neural network that we can train from examples of the type of signal we would be measuring that actually compresses the signals into a latent space that is much smaller, of the type that it's as small as the sparsity used to be, but it is actually capturing more of the structure and hence works as a better prior for the inverse problem, using which we could save even more measurements if it is a better prior. So the way it comes, we still have the y and the nonlinearity, and this last kind of matrix will, you can write it this way, but we think about it as the original data. And what was the original signal has actually this form. It's an output of a generative neural network itself. And the latent space to which we are going back is this Z star. So we have a model like that now where from samples of Y's and all the W's, we are reconstructing back the Z star. So mathematically, this is what it boils down to consider these signal processing problems with neural network generative priors. And, okay, under the assumption, again, we need to simplify to be able to do some math. So we need to assume that the weights are IID random, not learned. Learned, we can't do yet. So there is Max sitting in the audience who worked with me a few years back about trying to crack that. We did not manage. But at least when they are random, we have kind of nice theory, the approximate message passing, the state evolution, the phase diagrams. We wrote a couple of papers about that. Some interesting things happen. For instance, if we look back, this is a phase diagram of the phase retrieval with the IID prior, and this is the generative prior. It shrinks the hard phase. So doing it this way, it's as if the hard phase was becoming smaller. So we don't really kind of have full understanding of why it is so. It has been remarked in other papers. It seems that the hard phases are smaller when we kind of don't think about sparse signals, but think about generative neural network priors. Okay. Another kind of case where we use this idea is for, I see in the audience some friends who worked on the stochastic block model. So in the stochastic block model, usually we assume that the ground truth community structure is just IID labels. Okay? But we usually collect data where the nodes have attributes, and it is reasonable to think that there is a function from the attributes to the labels that we could learn. If we kind of could supervise, we could learn that function from the attributes to the labels, and that would give us a generative prior, and we would then be solving the stochastic block model, the community detection, under that assumption that actually these were not IID labels, but they were actually outputs of a generative neural network that was trained on the attributes and examples of known labels. And we call that the neural network stochastic block model. An interesting thing, there are interesting things happening in that version of the stochastic block model. For instance, the exact recovery threshold that normally needs the degree of the graph to grow logarithmically with the size of the graph for some like coupon collector problem reasons. And then only we can get exact recovery. With the generative prior, the exact recovery can come up at a constant degree. So that's kind of curious. We were surprised by that. And also this type of a model is a very cool benchmark, and people, the practitioner people actually use very related models to benchmark the behavior of graph neural networks that are kind of, out of the box methods to understand what's going on, what's the correlations in these type of data, but they are not doing as well as the optimal methods that now we can analyze. And kind of closing the gap is an interesting research agenda that could allow us to understand something about how to construct the graph neural networks more properly. So that's this thing about generative neural priors. So I think it's a beautiful idea, very, very popular in signal processing and very practical. I was saying yesterday that my former student who works for Philips, they were shipping a GPU and a new software to update the machines that they had previously to implement this in and get the improvement. The second assumption that I want to question, or at least here I only really have one slide, is this one of assuming that the data are IID Gaussian. Right? This clearly real data are not, they have structure. This is evidence. We somehow only started to question this maybe 4 or 5 years ago in this paper. But since then, there was a lot of work in that direction. And the kind of general idea here is that the theory that I presented to you generalizes. We can take Gaussians, generic Gaussian mixtures and Gaussians of generic covariance. And we can also show certain kind of generalizations of central limit theorems that show us that even when there is a little bit of correlation, for what concerns the test error, things do not change if you actually put in a bit of structure, but keep the same covariance matrix. So this goes under the names of Gaussian universality or spectral universality. The first paper that kind of brought that up very explicitly is this one by Andrea and Song, and then we kind of followed up. There were very nice works also by Yuelu. And this line of work kind of leads us to, you know, in the setting of the single layer neural network or a kernel method or a random feature neural network, you know, some learning curves of some real data actually look like those from this Gaussian theory. And okay, here I could have given an entire talk on kind of this line of work, but I'm just noting it here that, you know, we thought about going beyond the IID Gaussian data, and it's a very interesting and active area, basically mathematically showing non-trivial generalizations of the central limit theorem. So the last thing that I want to say, and you know, it's good to end up, I think, with an open problem, is what is the, okay, there are obviously many challenges, okay? But I always like to think of the one that is the simplest. So what is kind of the simplest case where I don't know where you know, there is a well-defined question, still the same question, what's the kind of optimal performance, can it be achieved efficiently, where I don't know how to even non-rigorously give you the result. And it's surprisingly frustratingly simple. So we are still in this teacher-student setting, so even going back to IID data and IID priors, okay, so we don't need to be complicated our life with that. So what we know, I showed you things without hidden units, or with hidden units with the gradient descent was kind of a special case. But if you had order 1 hidden units in front of the dimensionality, is the same story. And this is something that was realized in physics a long time ago, and we kind of added the, say, you know, current look with the proofs on it a couple of years back. And the order parameters just become, if you have k hidden units, k times k matrices. So it's a little bit like when we look at rank k matrix factorization or k community detection, is kind of a similar type of complication that we know how to deal with. So everything goes through in this program, and you can draw the phase diagrams compared to gradient descents, etc. Another case where the number of hidden units would be much larger than the dimension, then the teacher function, because of central limit theorem, is reducing to a Gaussian process. Okay, it's central limit theorem kicks in, and functions like that can be optimally learned by linear methods or kernel methods. So that's again a regime where things are well understood. But a non-trivial regime would be, for instance, the one where the number of hidden units over the dimension is a constant, say 2 or 3 or half. So there, another number we have is the number of samples. So if the number of samples now is only linear in dimension, then we also understand things. And we know that this is kind of too few samples to be able to do anything non-trivial, so the optimal thing is to do linear regression. So that's, in a sense, a trivial regime. We have too few samples for things to be even possible in some non-trivial sense. We also know that the relevant and interesting regime is actually when the number of samples is quadratic with the dimension. From numerics, we see that. From kind of heuristic hand-waving arguments, we see that. But we don't know how to compute, say, the free entropy from which we would extract the optimal error or the optimal behavior of the algorithm. So we put that forward very explicitly in this last ICML paper, where again, the setting would be the following. Now we have k hidden units, dimension d. The teacher function is written above here with some nonlinearity phi, say, I don't know, ReLU, and Gaussian prior Gaussian data in the scaling where the width is proportional to the dimension and the number of samples is proportional to the dimension squares. So what these lines are, the yellow and green, is a performance of a linear method or of a kernel method, and is not working. It's not giving us a low error. The purple here is a gradient descent that at some sample complexity of 2.5 or something like that starts to learn the function exactly. But this is just a numerical simulation. I do not know how to write the asymptotic theory from which I would be able to extract the best test error. And I do not know what's the optimal algorithm here. The gradient descent likely is not, and I don't know which one it is. So that is I think, the simplest case for which this is entirely open, even disregarding the fact that, I relax the fact of wanting proofs or anything like that. We don't know how to do that. And why this is more difficult, because a priori it sounds like we should be able to do the replica method and it's kind of all the same in the class of the problems that I'm talking about. It boils down to our inability to solve extensive rank matrix factorization or extensive number of communities, community detection, or additional learning problem in the right scaling. So actually we thought 10 years ago that we knew how to solve it in this paper with Yoshiyuki Kabashima, who is probably the strongest person in these type of calculations in Japan, and Marc Mézard, who established this whole field, and me and Florent, we kind of proposed this conjecture, but it actually is completely wrong. So yes, also in physics, the conjectures sometimes are completely wrong, so that indeed the proofs sometimes are useful, and when we don't have them, we can miss things. Okay, so that's just to pragmatically say that I'm kind of arguing the theoretical physics here tells us all the answers, and it's not always true. This is embarrassing, but it's the reality. And then we wrote, and colleagues wrote a line of work where in special cases, we were trying to fix these things and also realize explicitly that what we did was just completely wrong. So the case we know how to solve is when there is Gaussian noise and Gaussian priors. So that's kind of an interesting line of work involving some matrix integrals called the HIEZ, Itzigson-Zuber something integral. But this is unsatisfying because in order to be able to say something interesting about neural networks, we would need a nonlinear activation, so not additive Gaussian noise, and we would need a non-trivial prior so that we can couple the layers together in a similar way that we are coupling them together when we deal with the generative priors. So I leave it today at this, I already talked to a couple of people that I talked about. I told, this Elhanan asked me that I should tell them what you should be working on. So you should be working on this. So I will leave it here with the 2 items that I want to cover tomorrow, and with a thank you from a summer school that we are sometimes organizing. These are some of our group members and former group members. Yesterday it was kind of an older work, but today I was presenting the work of many of those people, so that felt fitting to put them here.
Really interesting talk. I was wondering about the AMP algorithms. Kind of how do they compare computationally to typical tool that we would use in a neural network library? Should we expect that?
So on these very simple examples that I'm talking about, it's as fast, it's comparable. It doesn't, this question unfortunately doesn't make sense to like state-of-the-art neural networks because I don't know how to properly write these algorithms for the multi-layer case, right? That's part of the open question. So So okay, it's even worse than that. It's not that they are it's not that they are worse. They just don't even make sense, or don't even behave well, etc. But on these like just generalized linear regression models or these generative priors, they are largely comparable. I mean, then it would depend on the special case, right? And of course, I mean, the software was always optimized for the gradient descents and not for this. So you would have to do some additional work to make it scalable. But they are very distributable. They are essentially just matrix multiplications. They don't have anything complicated in them that would like clearly make them computationally less scalable on the cases on which they work.
You mentioned this example of the over-parameterized gradient descent for phase retrieval. I'm curious if instead maybe you just randomly initialize many different correctly parameterized networks. Would you expect there to be a threshold where one of these networks converges to gradient descent type algorithm?
Yeah, so this is a large system, so things concentrate, right? So I would expect that with probability 1, I will always get the same thing. And in order to get a better behavior, I would actually need to try exponentially many trials. So that would be losing a lot on the... So if I had exponential time, I could do it different ways. So that...
I'm wondering, are there sort of non-trivial problems where you would not expect the gap between approximate method passing and gradient descent?
So yes, right? I mean, the kind of existence of the gap to me came from the presence of this hard phase to start with. So for instance, if we were in the cases where there is no phase transition or the second order phase transition, I would not expect to see any gap. Maybe gradient descent would be still suboptimal simply for the reason that the maximum likelihood is suboptimal as compared to the Bayesian marginalization. But if you ran the Monte Carlo or the Langevin algorithm aimed at the right probability distribution, that would be as good as the approximate message passing in those cases. So to me, it's linked to the presence of these first order phase transitions that in the phase retrieval they are there. Why should they be there generically in kind of the neural networks that we are working in? I of course don't know, right? I'm not even saying they are, but the property that we actually need them over-parameterized, to me suggests that, right, there is this suboptimality of the algorithm. So that kind of indirectly suggests that maybe underlyingly these phases are there. That's a speculation, of course.
So I do have a question. So when you did the generative prior, compared to the product prior, it reduced the size of your hard set. I was just wondering if you have a sense of if I change my prior in that way, this is going to change my hard region in that way. Like, is there some monotonicity or something like this?
Yeah, I would love to, but I don't know. Like even that, we were kind of surprised by that and thought maybe it was specific to the particular case we studied. But then Paul Hand actually came up with a paper in quite different setting where he saw the same. So no, I don't know, but I would love to know the answer to this question.
So does it mean that these results are very sensitive to the prior?
Yes, they are very sensitive to the specific case. Yesterday, somebody asked me, do you have some intuition to tell whether in a given system the transition would be of second order or first order, right? So that's the same question because reducing the first order is kind of going towards the second order. And we don't, in a sense that this leads to these fixed point equations. We need to investigate whether there are more fixed points or not. We have some like generic principles from experience, right? When there are higher order interactions, for instance, tensors, they tend to bring in the first order phase transitions, or when there is sparsity. Sparsity also tends to induce them, or some like clique or like small subcommunity or something like that. And when we also have a higher rank, such as Potts variables or higher rank matrix estimation, that also tends to enhance the first order phase transitions. But this is more really, examining like 30 different problems and looking at the zoology. I don't have anything more kind of tangible. So that's a bit frustrating.
That's one of your works where you shrunk the hard phase.
Yeah.
And essentially what happens is it came to essentially two connected domains, and like that met at a point which is indexed by some variable, I think rho. What was like the mathematical meaning behind that?
Yeah, sorry, I was not really like explaining in detail what that was, right? The rho was the ratio between the dimension of the latent space to which I'm reducing it and the original dimension of the signal. So I'm kind of comparing it to the sparsity, right? The number of bits I need to represent a rho sparse signal is the same as the number of bits I need to represent this latent space. So I'm kind of comparing these two rows, but they are two different things. So that was the rho. The alpha is the same. That's it. Okay.